Hydrogen bond is an intermolecular force in which the electropositive hydrogen atom of one molecule is attracted to the electronegative atom of another molecule. And in this case, our electropositive being hydrogen here. And so in other words, in any hydrogen bonding, the reason as to why it's called an hydrogen bond, there has to be an electropositive hydrogen atom. Then in water, the electropositive atom is hydrogen, while electronegative atom is their oxygen. Therefore, you can see here, we have electropositive and partially negative here, partially negative. Now, this one should be positive, partially positive here. This one now. Then this one is going to be attracted to this one, which is positive here. So then an hydrogen bond is going to develop between this and this. So electronegative and electropositive, then an hydrogen bond. So this is the concept that is making water to have high melting point and high boiling point compared to hydrogen sulfide, which is made up of what we call molecular van der Waals forces, where this one will be having a hydrogen bond. So weak van der Waals forces are weak forces of attraction molecules between molecules or atoms, which exist only when particles are close together. Hydrogen bond, you should note that hydrogen bond is stronger than the weak van der Waals forces, but it is never stronger than covalent bond. Covalent bonds are stronger than hydrogen bond. So if you are to compare these three in the hierarchy of strength, then you have what we call covalent, followed by hydrogen, then followed by weak van der Waals. So the order, so this is decreasing strength. So we are decreasing in strength here. So that's something we really need to note. The influence of hydrogen bonding can also be seen in something called ethanol, which is an alcohol, and what we call dimethyl ether. If you try calculating their relative molecular mass, you are going to find that both of them have got 46 as the relative molecular mass. But then again, if you look at ethanol, ethanol has got what we call alcohol in it. Sorry, hydrogen bonding, C5H5OH. Now, when you look at that, so this is the electronegative, so it's OH. Now the electronegative part here is this oxygen being bonded to electropositive here. So this is what we call, this is what's going to contribute to hydrogen bonding. So between this hydrogen and this electron, we'll be having several of them. We'll be having another one here. Then another alcohol will be having that one here. With an O somewhere here. Then we have CH5C2. So that there's going to be an attraction here. There's going to be an attraction there. Therefore, there's going to be development of hydrogen bond. So when that happens, we are going to have high melting point and high boiling point in ethanol as compared to dimethyl ether. So the methyl ether has got boils at negative 24 degrees, while ethanol boils at 78. And this is because ethanol has hydrogen bond as the intermolecular forces, while the methyl ether has weak van der Waals forces as the intermolecular forces. Now, considering these two examples, and there could be several examples that are going to follow this same suit. But to your level, these are the examples that are going to be used for comparison. But now, when you find such kind of chemistry, when you find such somebody just asks you, comparing two with relative molecular mass, then one thing you should look at is whether there's an hydrogen bond there or not. An hydrogen bond, there has to be an electropositive element, atom, which is hydrogen in this case, and any other electronegative element or other atom. The example of water, hydrogen sulfide, ethanol and dimethyl ether are examples of comparison between hydrogen bond and van der Waals process. Most molecular substances are, however, insoluble in water. Some of them, most of them are insoluble in water, but some such as sugar, ethanol and ethanoic acid are soluble, and the reason as to why these are soluble is because of what we call the presence of hydrogen bonding. So the presence of hydrogen bonding makes these substances soluble in water. Remember, all these three, sugar has got that one, ethanol has got that one, while ethanoic acid also has got hydrogen bonding. So there's going to be an attraction. Now, the next thing we are going to consider here is what we call giant covalent structure or giant atomic structure. Now, sometimes we find that the covalent bonding, most of the studies we've done today in this covalent bonding is studies of substances that turns out to be molecular substances. But we are going to find that some of them do not necessarily need to be molecules. Some of them do not, like we are going to see in some of the cases. In some substances, the structure consists of indefinite number of atoms which are all covalently bonded together. The pattern reveals itself and fits in all directions. A good example of such substances include diamond. We are going to look at graphite. We are going to look at silicon oxide. Now, what about diamond? A diamond and graphite, the two which have been considered here, diamond and graphite, these are called allotropes of carbon. What are allotropes? An allotrope, these are different forms of an element in the same physical state. Like for example, we have what we call diamond and graphite. These are different forms of carbon. They are different forms of carbon. Allotropes are different forms of elements. Now, which in this case, the allotropes we are dealing with is diamond and graphite. Even though there's more allotrope of carbon, but in this case we are going to deal with these two. So different forms of an element. And different forms here, example would be diamond and graphite, and in the same physical state of an element. And our element here, different form, diamond and graphite, of an element. And this element we are dealing with here is the carbon being the element in the same physical state, which with the physical state we are talking about here, we are both solids. So these are allotropes of carbon. So diamond, what is diamond? Diamond, in diamond we find that carbon has got what we call 4 electrons. 4 electrons in the carbon. Now, we find that these 4 electrons are going to be surrounded by more 4 electrons. These 4 electrons are going to be surrounded by 4 more electrons to make it complete from other 4 carbon atoms. From other 4 carbon atoms. And as the bonding continues, they are going to form and share a structure called known as octahedron, and I'm going to show you in a while. And in this case, as you can realize that this is now a covalent, 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 covalent. So this is going to contribute to building, or rather to a very strong covalent bond. And this is going to make diamond to have very high boiling point and melting point. Actually, diamond is the hardest substance ever known on this earth because of these strong covalent bonds that are going to result from four bonding of the 4 electrons with other 4 electrons from different carbon atoms. So you find that one carbon atom is surrounded by other 4 carbon atoms. And this is what we call the hedral structure of diamond. So this is, as you can see, we have carbon atom, then we have the covalent bonds here. So diamond is having the strongest, substance. The pattern repeats itself. Diamond, in this structure, we find that all the valence electrons have been used in bonding. Therefore, diamond is a poor bonder to steel because there's no localized electron. It's the hardest substance, not because of 2 reasons. One, the atoms are completely packed, and the strong covalent bond that exists. And therefore, the melting point is very high, 3,700 degrees centigrade. Now, we're going to stop there. Then, next time, I'm going to come in, we are going to discuss about graphite. Have a good day.